Welcome, everyone. I would like to express that we are very grateful for this interest in the topic, and thank you very much for taking the time to join us for this webinar session today. My name is Katharina, and I will moderate today's webinar with the subject Mastering Aluminum Alloy Preparation for Electroless and Electroplating. First and foremost, I would like to introduce to you Dr. Alexandra Yevtuchenko and Shakil Akhtar, who are our speakers and subject experts today. Dr. Alexandra Yevtuchenko, Global Application Manager, Wear-Resistant Coatings, holds a PhD in Physical Chemistry and has more than 16 years of experience in the characterization of metallic coatings and the tailoring of specific material properties. In 2014, she joined MKS Artotech R&D team as a scientist focusing on development of new processes for wear-resistant coatings. Alexandra's extensive experience ranges from in-depth know-how in corrosion science, electrochemical characterization, development of new galvanic processes, and improvement of processes as per customer needs. And then we have our second speaker, Shakil Akhtar, Global Product Manager and Business Development Manager for wear-resistant coatings. He joined MKS Artotech back in 1988. And as a specialist in electroless nickel plating, he has extensive knowledge of surface finishing, including functional chrome. During his career, Shakil has held various positions such as R&D development chemist, product specialist, global application manager, technology manager, and product manager for wear-resistant coatings. He has gained extensive international experience serving customers around the world and was based in Singapore for 6 years. In his current position, Shakil oversees the global Artotech product range and business development opportunities for wear-resistant coatings. Welcome, Alexandra and Shakil. A couple of words about the webinar before we start. The webinar will be divided into two major parts. We have around 35 minutes presentation and 10 minutes Q&A session. I encourage you to raise questions during the presentation, and therefore please use your Q&A function, which you can find in your control panel. Keeping confidentiality, we will not publish the questions, so you can only see the question which you have posted yourself into the section. We will try to cover as many questions as possible during the planned Q&A session at the end of the presentation. Of course, if time allows, we will answer all questions right away. Also, Alexandra and Shakil will be available after the webinar session to reach out to you via email. Last but not least, there will be a recording available after this webinar session, and we will let you know when it is released and then send the link by email to you. So now let me hand over to Alexandra and Shakil, and please enjoy the session.
Thank you, Katharina, for a very nice and kind introduction, and welcome from my side. So today, during the webinar, we will show you some properties of aluminum and its alloys. Then we will shortly show how to tailor pretreatment processes for different types of alloys. Also, we will discuss some functions of pretreatment steps like soak cleaning, alkaline etching, desmarting, zincating, rinsing. Then we will shortly talk about electroless nickel strike. And finally, we will show you some plating processes and go to the summary. So let's start from properties of aluminum alloys. Surface finishing to aluminum is used in many industries and for many applications. Due to its unique physical properties, for example, like extreme good malleability, it is possible to manufacture very complicated geometries, and that's why this element, this metal, is so important. For example, you can see that fuel pumps can be produced, turbocharger wheels, scroll compressors. At the same time, for example, properties like extremely good electrical conductivity allows to use this metal in bus bars, for connectors, for rigid memory disks, and also for many other applications. So let's talk a little bit about the properties. As I already mentioned, this metal is very soft and light. It is ductile and malleable, so that you can manufacture really complicated parts. It is excellent conductor for electricity. And mechanical properties are adjustable over wide range.
Today's webinar with the subject Mastering. Welcome everyone. I would like to express that we are very grateful for this interest in the topic, and thank you very much for taking the time to join us for this webinar session today. My name is Katharina and I will moderate today's webinar with the subject Mastering Aluminum Alloy Preparation for Electroless and Electroplating. First and foremost, I would like to introduce to you Dr. Alexandra Yevtuchenko and Shakil Akhtar, who are our speakers and subject experts today. Dr. Alexandra Yevtuchenko, Global Application Manager, Wear-Resistant Coatings, holds a PhD in Physical Chemistry and has more than 16 years of experience in the characterization of metallic coatings and the tailoring of specific material properties. In 2014, she joined MKS Artotech R&D team as a scientist focusing on development of new processes for wear-resistant coatings. Alexandra's extensive experience ranges from in-depth know-how in corrosion science, electrochemical characterization, development of new galvanic processes, and improvement of processes as per customer needs. And then we have our second speaker, Shakil Akhtar, Global Product Manager and Business Development Manager for Wear-Resistant Coatings. He joined MKS Artotech back in 1988. And as a specialist in electroless nickel plating, he has extensive knowledge of surface finishing, including functional chrome. During his career, Shakil has held various positions such as R&D development chemist, product specialist, global application manager, technology manager, and product manager for wear-resistant coatings. He has gained extensive international experience serving customers around the world and was based in Singapore for 6 years. In his current position, Shakil oversees the global Artotech product range and business development opportunities for wear-resistant coatings. Welcome, Alexandra and Shakil. A couple of words about the webinar before we start. The webinar will be divided into two major parts. We have around 35 minutes presentation and 10 minutes Q&A session. I encourage you to raise questions during the presentation, and therefore please use your Q&A function, which you can find in your control panel. Keeping confidentiality, we will not publish the question, so you can only see the question which you have posted yourself into the section. We will try to cover as many questions as possible during the planned Q&A session at the end of the presentation. Of course, if time allows, we will answer all questions right away. Also, Alexandra and Shakil will be available after the webinar session to reach out to you via email. Last but not least, there will be a recording available after this webinar session, and we will let you know when it is released and then send the link by email to you. So now let me hand over to Alexandra and Shakil, and please enjoy the session.
Thank you, Katharina, for a very nice and kind introduction, and welcome from my side. So today, during the webinar, we will show you some properties of aluminum and its alloys. Then we will shortly show how to tailor pretreatment processes for different types of alloys. Also, we will discuss some functions of pretreatment steps like soak cleaning, alkaline etching, dismuding, zincating, rinsing. Then we will shortly talk about electroless nickel strike, and finally, we will show you some plating processes and go to the summary. So let's start from properties of aluminum alloys. Surface finishing to aluminum is used in many industries and for many applications. Due to its unique physical properties, for example, like extreme good malleability, it is possible to manufacture very complicated geometries, and that's why this element, this metal, is so important. For example, you can see that fuel pumps can be produced, turbocharger wheels, scroll compressors. At the same time, for example, properties like extremely good electrical conductivity allows to use this metal in bus bars, for connectors, for rigid memory disks, and also for many other applications. So let's talk a little bit about the properties. As I already mentioned, this metal is very soft and light. It is ductile and malleable so that you can manufacture really, really complicated parts. It is excellent conductor for electricity, and mechanical properties are adjustable over a wide range by alloying different elements, which we will talk later about. Aluminum surface is covered with oxide layer, and this is extremely important because it makes this metal really, really corrosion resistant in different surroundings. And last but not least, this is non-magnetic metal. That's why for certain kind of application, it is quite important. When we are talking about alloying elements, then we have different types of alloys. So for example, if you have type 1000, you may suggest you have near pure aluminum. If you have type 2000, there is a copper alloy, which gives you property like strength and machinability. Type 3000 contains manganese for better formability, type 4000 silicon, type 5000 magnesium to improve hardness and corrosion resistance, type 6000 magnesium and silicon, type 7000 zinc, and type 8000 some other alloying elements like, for example, lithium. So we know already very good properties of this metal, but what is important else? Very important is to clean the substrate, because during fabrication, these metal parts undergo a variety of processes which produce contamination on the surface. And that's why we need to be sure that we remove all undesirable oils, soils, oxide from the surface. And doing that, we will provide the best performance on the final finish, whether it is functional or decorative. So which type of contaminations do we have on aluminum surface? These may be grinding compounds, polishing compounds, metal fines, machining fluids, metal working lubricants, welding and brazing fluxes, oxide and coolants. And all these we need to remove and to clean the part. Here on the slide, just to show you what would happen or what can happen if the pre-treatment is not effective enough. For example, what you can see some pitting on the surface. This is, you can see on the right-hand side on the top left. Then you can have something like delaminations, peeling of the deposit. And this is, of course, really undesirable. And at the end, what will happen? Your part will have poor corrosion resistance, and in worst case, there will be contamination of the bath with aluminum. Here on this slide, you can see basically the microscopic picture of one pit on the surface, aluminum surface plated with high phosphorus electroless nickel. You can clearly see the gas pitting, and you may imagine that it looks like something is underneath of the pit. So it looks like there will be delamination. On the right hand side, you can see basically that in this case, this is electroless high phosphorus nickel process. You can see that the layer just mirrored the substrate, and all the defects which you have in the substrate will appear also on top of your coating. Also, you may see some inclusions, some defects, and of course, this is not good. But when we are talking about cleaning, what do we mean? Basically, there are two different important things. We can talk about cleaners. So these are like chemical processes or electrochemical processes. So these are solution, and which kind you choose, it depends, of course, of chemical nature of contamination. Then also it depends on the concentration, and also you can change the concentration of your cleaner, you can change the temperature, you can adjust immersion time, or you can play with agitation to improve the cleaning. Very important is not to forget about rinses. We basically suggest to use rinses after each pre-treatment step, but in the same time doing that, there might be some drag in of chemistry from previous processes, and this is also the contamination factor which may impact the cleanness of your rinses. Then it depends on the temperature. For example, if the ambient temperature outside is quite high and you need, for example, to process some parts which plated with elements which can passivate quite fast, then might be that you need either to play with the temperature of the rinses, or maybe you may need even to acidify a little bit. Important is time in contact with rinse waters. Again, it depends on the metal you plated. Important is agitation and also flow pattern. So let's talk a little bit about tailored surface preparation. Basically, on this slide, you can see the pre-treatment process, typical pre-treatment process for electrolytic nickel plating, for example. So here, what we suggest, you need to start from the degreasing. You need to remove organic materials and soil from the surface, and this will then allow uniform etching in the later steps. For this, for example, one of the process of choice we offer, this is Uniclean 151. The second step would be etch. Either this is alkaline or acidic or both, to remove some organic inclusions from the surface by etching of the substrate and to roughen the substrate, the surface, to provide better adhesion later. The next step would be dismatting. So you remove this insoluble residuals which left on the surface by the previous etching step, and then we can go for the Syngate process, which in this case is Alumsil 611, which is cyanide-free process and will be presented later. And doing that, you remove oxide layer from aluminum substrate and replace it with zinc. You can use either one or two steps. We will talk about this later. Then there is a nickel strike optional step. Why optional? Because basically we also have some processes which are developed especially for the Syngate step to be tolerant to zinc. And if we are talking about electroless nickel plating, more or less you have very comparable steps. However, in this case, we suggest always to use double zincate, because it will provide you more dense and thin zincate layer. And this is basically also the precursor stands for better adhesion later. In this case, for electroless nickel, also we propose to use nickel strike, which is Nichem 1111. And if you have this process, this will basically help you to prevent, drag in of zinc into your electroless nickel plating bath. Also, in this case, we have some processes which allow you not to use nickel strike, and in some cases this will just speed up the processing time of the parts and finally will bring you a benefit. So this was a very short introduction from my side, and now I would like to hand over to my colleague Shakil. Thank you.
Thank you, Alexander. And first of all, good day to everyone from my side. I will now take some time to go through the various steps which are involved in the preparation of the surface prior to plating. So the first step in a generic cycle, which Alexander has already presented in the previous slide, is the soil cleaning step. The function of this step is to remove all types of organic soils to remove all contaminants from the surface, lubricants, and cutting fluids. And depending on how the components were manufactured, you may have some embedded materials. This would be in the case of parts which have been stamped, so that during the stamping process, some organics on the surface may be embedded into the surface. And also, if parts are casted, then you could have potentially mold release compounds on the surface of the casted parts. So we need to remove all these types of contaminants from the surface so that we can ensure a uniform surface etching of the material in the subsequent process steps that follow the soak cleaning step. The most important criteria for this process step is that it needs to be a non-etch soak cleaner, and it needs to effectively remove the contaminants from the surface. As an immersion time can be more than sort of 5 minutes, it's important that the cleaner is a non-etch cleaner on the aluminium surface. For this step, we offer a UniClean 151 product, which is a universal cleaner for all types of aluminium alloys. This means you can treat wrought materials as well as cast materials. Soak cleaning formulations use strong wetting agents or surfactants to solubilize the organics from the surface, as is illustrated in the slide on the bottom right hand corner. So it's important when we are formulating that we don't use any materials in the formulation which exacerbate the etching mechanism, and we need to ensure that a selection of the right wetting agents and surfactants are chosen so that we can remove the most tenacious type of contaminants from the surface. So then on the next slide, we look at the second step of our pre-treatment sequence, which is the etching step. This is a very important step because the soak cleaner has already done its job by removing the contaminants which were directly on the surface, but the soak cleaner will not be able to remove any oxides from the surface or any embedded material in the surface. So during this step, the alkaline etch bath formulation is usually based on sodium hydroxide. It's a highly alkaline bath, and commonly used are based on sodium hydroxide with some complexes so that when we're dissolving the aluminium from the surface, we also complex this to avoid sludge formation. And the most important thing about this etch process is that it must provide uniform dissolution of the aluminium surface, and it does this as indicated by the chemical formula shown. Please note this step only attacks the aluminium but does not dissolve the alloying metals or elements in the alloy, such as silicon, copper, magnesium, manganese, as was mentioned by Alexander in the previous slides. So these are left behind and create a smut on the surface, which can be a light gray color to very dark black color, depending on what type of alloying metals are used within the aluminium. The most problematic type of elements that create the most smut are silicon, copper, and that's because usually you have a very high concentration of these alloys elements in the alloy. Silicon can range from 2 to 3% up to 14% in the alloy, in some alloys, and copper can range from 1 up to 4 to 5%. So these tend to be the most problematic. The surface topography during the etching process can become more rougher, as is indicated by the atomic force microscopy image shown. On the original parts and after the alkaline etching, you can see the big difference between the before and after the etching process. The other thing is we must take special care for cast materials because during the casting process, the aluminium surface can have quite a lot of cavities develop under the cast skin. The cast skin usually is about 200 microns in thickness, so we have to take special care that we don't break this skin and expose the cavities underneath, because any cavities we generate then will show up as either pits in the surface or will retain some of the chemical residues from the previous steps, and this can lead to corrosion and adhesion failures. Next slide. On the next slide, we see the desmutting step. So during the alkaline etching, as I already mentioned, we will generate quite a lot of smut on the surface, and this has to be removed before we can do anything else with the parts. So the purpose of this particular step is to remove the smut residues created in the second step, and also any insoluble materials which may have been exposed by the alkaline etching step. So we need to remove this. Sometimes you can get like silicon particles, and depending on the quality of the substrate, it can expose certain type of materials on the surface, which then need to be removed. Otherwise, we create roughness or non-plating around those sort of protrusions. In this step, very critical is that we need to adopt the formulation of the desmut to the type of alloy that we are treating. So, for example, if it's got a very high silicon content, then we need to make sure that we have sufficient materials in our formulation to take care of the silicon. Or if it's got high copper, then we need to make sure that we have the relevant substances in our desmutting step to remove those. Desmut processes are mainly based on a combination of nitric acid, sulfuric acid, and fluoride, and these can be altered according to the alloy that you are treating. Atotech offers a nitric-free based process also, and this one we call Alamech LF. But I have to state here that in terms of effectiveness, the nitric acid or triacid type of desmuts are the most tolerant to a wide variety of alloys. But for sure, Alamech LF and Alamech NN, which is the non-nitric process, is very effective on the simpler alloys. Then on the next slide, we can see the difference in the etching behavior of the alkaline nitric acid based steps versus those based on acidic etching and non-nitric options. And the two images you can see on the left hand side is the nitric based and alkaline etching step, and on the right hand side you can see the acidic etch using also the nitric free desmut process, and you can see the huge difference in the etching behavior of the two type of systems. You have a much higher etching rate from the alkaline etch and nitric acid desmut versus the second option, which is nitric free and using acidic etching. And this can have an impact on the adhesion depending on what type of alloy you are processing. Next slide. On the next slide, once all contamination and oxides have been removed from the surface of the aluminium, we need to prevent the reoxidation of the surface. Aluminium is quite a reactive metal, so as once you remove the oxide and it's exposed to the atmosphere again, it will rapidly form an oxide coating. And oxide coatings are detrimental in terms of ensuring that we achieve the best adhesion. So we achieve this by covering the surface with a thin layer of zinc to prevent the reoxidation process, and we do this using a zincate process. The deposition mechanism by which the zinc is deposited is called displacement reaction, as shown on the slide. The zincate bath is alkaline with a high pH and contains sodium hydroxide, and aluminium is dissolved and then it's replaced with the zinc atoms. So for every 2 aluminium atoms that we dissolve from the surface, we deposit 3 atoms of zinc onto the surface. The formulation of the zincate can include iron, nickel, copper, and thus the composition of the film normally includes not only zinc, but will have traces of iron, nickel, and copper. And these are important, as we see in the subsequent slides coming up. So in the next slide, for the zincate step, Atotech launched its AlumSeal 611 process about 5 years ago to provide a very thin zinc coating to ensure we minimize the dragging of zinc into a main plating bath. And by reducing the zinc dragging, we can assist to extend the bath life of the plating process. This particular process is a cyanide-free single additive process used for both makeup and replenishment. The process gives best performance when used in combination with a Nichem MP1188 electroless nickel process, which also is specially formulated to tolerate higher zinc contamination limits. And we will discuss this more in the subsequent slides. The combination of both these processes eliminate the need for an electroless nickel strike in the pretreatment sequence. So on the next slide, for most electrolytic processes, a single zincate coating is usually sufficient to achieve the desired adhesion properties. However, for electroless nickel deposition, best adhesion is achieved when double zincate is applied. The first zincate coating must be stripped. This can be done either in using 50% nitric acid or proprietary non-nitric acid processes like the Atotech AlumSeal Activator BD, which prevents NOx fumes, eliminates nitric from that particular process step, and is also much safer to use in comparison to the nitric acid. On the previous slide, I mentioned that the zincate film is composed not only with zinc, but also includes the alloying elements such as iron, nickel, copper. During the stripping, the zinc is completely removed from the surface, but the alloying metals usually migrate into the aluminum surface and form a very thin sort of intermetallic layer. And this intermetallic layer influences the growth of the second zincate film. So on the next slide, we see that after the first zincate film, the second coating is applied. The first coating tends to form very rapidly, and therefore its structure is usually thick, spongy, and rough looking. In appearance, it looks quite dark gray, and we normally employ up to 30 to 60 seconds of immersion time to achieve the first zincate. However, the second zincate coating, which forms much slower due to the presence of the intermetallic layer inhibiting the growth, and is structurally more compact and smaller grain size structure, and is much thinner compared to the first zincate. And Immersion time for the second zincate is usually half the amount used for the first coating. The difference in thickness can be 6 to 10 times lower compared to the first coating, and you can see the difference in structure in the atomic force microscopy images shown on this slide. On the you can see that the roughness of the second zincate is much lower. Grain structure is much smaller compared to the first zincate. On the next slide, we can see the structural difference in the two type of coatings more clearly, and you can also see that the composition of the second layer, which shows a higher concentration of the alloying elements in the coating compared to the first coating. It is almost double the concentration in alloying metals compared to the first coating. The SEM image shows the difference in the structure of the film. The first coating is rough and very granular, whereas the second coating is much smoother in structure. On the next slide, the electroless nickel strike bath is used, and the function of this is to dissolve the aluminum from the aluminium surface and deposit a thin layer of nickel phosphorus coating on the freshly exposed aluminium surface. By doing this, we eliminate the carryover of zinc into our main electroless nickel plating bath. The alkaline electroless nickel baths, which are used as strike coatings, are usually based on ammonium salts. So they have a pH of around 9 to 9.5. And these baths, you have to ensure that you have very good pH control, because pH below 9 or above 9.5 can lead to issues related to adhesion. So it's important to maintain. This is the sort of sweet spot of operating this process, which is 9 to 9.5 pH. These alkaline baths have strong complexes in the bath, and they are more tolerant to the zinc contamination. And they can hold up to 2 grams per liter of zinc in solution before we start seeing any negative impacts on the adhesion of the coating. The zinc usually impacts the stress in the deposit, and hence stress has an impact on the adhesion. So this is why it's important that we control the amount of zinc that's going into the electroless nickel plating baths. So Atotech offers our NICHEM 1111 process, which is a low P EN strike bath. With this, we apply approximately 0.2 to 0.5 microns of the nickel phosphorus layer, which is fit for most purposes to reduce zinc carryover into our main electroless nickel and improve the adhesion. On the next slide, I mentioned earlier that Atotech offers the package of Alum-Seal 611 zincate with NICHEM MP 1188 electroless nickel process, which is a mid-P process. And for most aluminum, most of the applications require the use of a mid-P process. But using this combination, we can extend the bath life of the electroless nickel process. The zincate process produces a lower thickness of film, and this in combination with the electroless nickel process, which has a higher tolerance to zinc contamination, we can extend the life of the electroless nickel bath. Normally, electroless nickel baths without electroless nickel strike usually last between 3 to 4 metal turnovers, because by this stage the zinc contamination level can increase to 100 to 120 milligram per liter. But with the 1188 process, this can tolerate up to 200 milligram per liter of zinc in the plating bath. Thereby, using a combination of LMCL 611 and 1188, we can extend the bath life to 6 to 8 metal turnovers without using an electroless nickel strike. Then on the next slide, a step which in a typical plating line, a step which is overlooked usually and is a critical step in the process, and that is the rinsing steps. So special attention should be paid to this between each process step. Usually we end up, if we don't take care of this step, we can end up with a lot of reject rates from the plating line. So to ensure unnecessary rejects, rinsing is very critical. With good rinsing, you prevent contamination from the previous steps, and thereby you extend the life of the subsequent process. So prolonged immersion time should be avoided in the rinse steps, and that's because aluminium is a very reactive metal, and you will increase the risk of corrosion products forming if it's left in water for too long. All rinses should be circulated with sufficient flow rates of fresh water, and we highly recommend the use of counterflow rinses in any plating line, not just for aluminum plating. Temperature of the rinse water should be above 30 degrees should be avoided because higher temperatures you have a higher risk of forming corrosion products on the surface. Long transfer times between the steps should also be avoided because the longer the transfer time, the more risk you have of the chemistry that's on the aluminium surface reacting with the aluminium and forming corrosion products. On the next slide, once the surface of once the surface has been prepared correctly, it is ready for applying the various types of metals such as cyanide copper plating, alkaline copper plating, electrolytic nickel processes, whether you are plating semi-bright, nickel sulfamate or bright nickel. It's also electroless nickel, tin, silver, zinc, nickel, etc., etc., etc. For most applications, when using electrolytic platings, a single zincate is usually sufficient, but a double zincate coating provides superior adhesion and definitely recommended for electroless nickel plating. Some of the alloying metals in the zincate film also assist to get better initiation from the electroless nickel when applying double zincates. And then to summarize on the next slide, we can say that aluminium and its vast variation of alloys can be successfully plated with various coatings when the surface is properly cleaned to ensure all traces of contamination and oxidation from the surface are removed thoroughly. Atotech has over 4 decades of experience in developing tailored solutions to cater for specific types of aluminium alloys to ensure the best possible adhesion of the required coating is achieved. And you can contact us for recommendation on process optimization for your application, and we can assist with sample plating also in our numerous technical centers which are spread over the whole world. On that note, this ends our presentation, and I would like to thank everyone present in this webinar today for your valuable time. And we are now open to your questions. So thank you.
Thank you very much, Shakil. Thank you, Alexandra and Shakil, for this great presentation, and we will now proceed with our Q&A session. I would like to remind you that we will cover as many questions as possible during our Q&A session, and all the rest will be answered by Alexandra and Shakil after the webinar via email. So let's not waste any more time and start. First question. Is there a universal pre-plating procedure for all types of aluminum alloys?
Let me answer this question, Katarina. Well, it is difficult to find a pre-plating procedure which is equally satisfactory for all types of aluminum alloys, because the various alloys and products have different electrochemically due to the different compositions and metallurgical structures. So basically, when elements are added for alloying purposes, they may appear in aluminum alloy in several different forms. So they may be in solid solution in the aluminum lattice, be present as microparticles of the elements themselves, or be present as particles of intermetallic components formed by combination with the aluminum. So the several solution matrix which may occur in commercial aluminum alloys may have different chemical reactivities and electropotentials, and their surfaces may not respond uniformly to various chemical and electrochemical treatments. And in addition, of course, the response may be influenced by variations in the microstructure of different lots of products of the same alloy. So finally, the electroplaters need to know exactly the alloy they are working with to be able to choose correct procedures because and correct processes for that, because one are more aggressive or less, and the finishing of the part is different. So for example, roughness requirements at the end are very different. But that's why, as I mentioned, you need to know exactly which alloy you're working with. And we as Atotech MKS may offer best pre-treatment solution for you at the end. Thank you.
Thank you very much. Next question. Why is the nickel strike required for aluminum plating?
I will take this question. And part of it I've already answered in the presentation, but nonetheless, I will reiterate. A strike, the function of the electroless nickel strike is basically to try and extend the bath life of the subsequent plating process. So whether this is electroless nickel, electrolytic nickel, or some other plating process that you are using. And we do this by the fact that these nickel strike baths are specially formulated with a certain type of complexes to be more tolerant towards the zinc contamination that's being dragged in from the zincate process. So in these plating baths, these can tolerate up to 2 grams per liter of zinc. And if we're talking about the tolerance level of zinc in a electroless nickel plating bath, the maximum zinc that an acidic electroless nickel bath can tolerate usually is between 100 to 120 milligram per liter. And once the zinc contamination reaches this level, it causes tensile stress within the deposit. And this tensile stress, once it exceeds a certain limit, can have negative impact on the adhesion of the nickel phosphorus coating on top of the aluminium surface. So to try and extend the bath life of these electroless nickel baths, we introduce these electroless nickel strike baths in between the zincate and the plating bath, so that bulk of the zinc can be dissolved in this, and we put a thin, very thin layer of nickel phosphorus coating on the surface to prevent further oxidation of the surface before going into our main electroless nickel. So this is the main reason for using an electroless nickel strike. But Atotech does offer an option where we have a zincate which produces very thin zincate films, so the amount of zinc dragged in is reduced. And we also have an electroless nickel process which has a higher tolerance to zinc contamination. So you can avoid using an electroless nickel strike, but in situations where there are no alternatives, then electroless nickel strike is highly recommended.
Thank you very